Okay, so last class I calculated the value of reaction force. Okay, so now once you got the value of reaction force, you need to find out what is the shear force as well as bending moment. So you're going to get over the section. Okay, now we have calculated reaction force at support A. Okay, so as 17 kilonewton, and at B you have got a 23 kilonewton. Okay, 23 kilonewton. I think you got the concept how to calculate the reaction force. So taking the moment. So now you need to consider any one point here, any point which is at a support, which is at a support. Then you calculate the moments and equate it to 0 for equilibrium condition, right? So based on this, as well as the equilibrium condition of forces, you got the reaction force RA as to 17 kilonewton and RB as 23 kilonewton. So now let us draw the diagram, the free body diagram of the simply supported beam. So with the reaction force as well as the forces acting on the component. Now this is what a reaction force RA, which is 17 kilonewton. Okay. You have some load here. You have some load. So now this is what reaction force RB. This is 23 kilonewton. I think this load is 30 kilonewton. This load is 10 kilonewton. Now regarding dimensions, so 3 to 10. Okay. So now this is what a 3 meter here. You are going to get this as a 5 meter, and you are going to get this as a 2 meter. This is what support A and support B. Now, if you consider some portion of the beam, if you consider some portion of the beam, so let us take a example. Now I will take one small section here. Okay, I'll take a section. Now this is our left hand side, this is our right hand side. Now what is the effect of load? What is the effect of load on left hand side? React. 17 kilo. Okay, so 17 kilo, what it is trying to do? It tries to push up. Now this is what it's try to push up the left hand side portion in upward direction, right? Yes. Okay, left hand side portion in upward direction. So now what about the load is there on right hand side? So it has a summation of two loads. One is vertical load acting in upward direction, another one is vertical load, those are acting in a downward direction. No, if we consider one more section, okay, let us take an example. So I will have a section here. Now let us assume this has been cut into two pieces at a section XX. At a section XX. Okay. Now I'll draw the diagram for this section, which is there to be on left hand side as well as on right hand side. Okay. Now, so now in this case, has a reaction force of 17 kilonewton. Okay. So let us take section this as a AA. Now this try to push up this left hand side portion in a upward direction. Okay. This left hand side portion in upward direction. Okay. So then the other forces which are there on right hand side, if you go on for calculations. Now let us take the right hand side. What is the forces are going to act? So 10 kilonewton is acting in a downward direction. 30 kilonewton is acting in a downward direction. So 23 kilonewton is acting in a upward direction. Now how much you are going to get here? You are going to get a 17 kilonewton, right? You are going to get a 17 kilonewton. So what is the effect of 17 kilonewton here? So the 17 kilonewton is try to push the component in downward direction. You can just observe here. 10 is downward direction, 30 is a downward direction. So total load which is going to act in a downward direction is a 40 kilonewton. Okay. So now you have a support. This support is carries the 23 kilonewton that try to push in upward direction. So now the net force which is going to act on this particular portion is of 17 kilonewton. So which is try to push the element in downward direction. Are you agree? Are you agree? Now on this side, now on this left hand side, the reaction force is there. It try to push the component upward direction. On another side, so the force which is going to get by the summation of the reaction force as well as the loads. Now this try to push the downward direction. Suppose, so if the forces are acting in upward direction as well as downward direction, so you need to consider the sign convention. You need to consider the sign convention. Okay. So now you got, so left hand side what happens? So it's going to push up. Okay. Now this is what left hand side, and on right hand side, it try to push it down. Suppose, let us take, now I made a section, okay, so which has been there at 2 meter from this support load. Okay. That means particularly this section is 4 meter from this left support, from this left support. Now in this case, as it does not have any locations here in first case, okay? So on first case, as it does not have any locations, okay, so you just consider only one side. You got a load. On this side also you got a load. Okay, but we have not considered the movement effect there. We have not considered the movement effect. We have not considered movement effect there. We just calculated the forces which are there. So causing the component to be move in upward direction or in move in downward direction. So now in this case, what happens? Now let us take an section here, okay, which is to be at 4 meter from left hand support. So let us assume it has been cut into two pieces. Let us assume it has been cut into two pieces. Now to find the forces experienced by this section, so consider any one section. So as we done for first case. Okay, now let us take the left hand section here. So let us take left hand side. Okay, let us take left hand side. Now what is the transverse load you're going to get on left hand side here? Reaction force is how much? 17 kilonewton. Now and load is at 10 kilonewton, which is acting downward direction. So now what is the transverse experienced by the left side portion? How much load is going to act over the that particular left side portion? Someone give answer.
Seven, sir.
So it's going to experience 7 kilonewton. Okay. So what is the 7 kilonewton? 7 kilonewton tries to move this cut portion in upward direction. Try to move the cut portion in upward direction. So now let us consider the movement exerted by this left side portion at this section XX. Now movement experienced by this portion. So can someone give the answer? What is the movement it is experienced by the left side portion? How much? Now it is a location is 4 meter from left hand support.
28 kilonewton.
Pardon?
28 kilonewton meter.
28 kilonewton
Meter.
meter. 28 kilonewton meter. Check it once again. Check it once again. Just to place the sections. Just to place the sections and to find out how much you will get. No idea.
20.
Give the answer. Let us try whether it is right or not. We'll discuss.
20 Newton meters. Kilonewton meter.
20 kilonewton meter. Now let us look here. Now this is the section what you got. Okay, XX. Now this is about a reaction force. Okay. Now this is about a load which is there of 10 kilonewton. As I said, so distance is how much? It is a 4 meter here. Okay, 4 meter. Now this distance is how much? It's a 2 meter. Now, as you need to find out the movement experienced by this left side portion at this section XX. At section XX. Now, because of this RA, let us take you fix this point here. Okay, let us fix this point. Okay, now what is the effect of Ra on this beam? Okay. So what is the effect of this Ra on this beam? Whether this Ra force is try to push the beam in upward direction or in downward direction.
Upward direction, sir.
So now let us take this is try to make this beam in upward direction. Are you agree with this one? Right?
Yes, sir.
Okay. Now what is the effect of 10 kilonewton? Now this 10 kilonewton try to push this beam in a downward direction. Are you agree?
Yes, sir.
Okay. Now movement is to be calculated about the section here. Now you took a one point here. Let us go for this point as a BB point, small BB. Okay. Now what is the movement about this point of this load? It is how much? RA into 4. Okay. Let us take, if you take this as a making a clockwise movement, so if you take it as a positive, now 10 kilonewton, they try to make this in an anti-clockwise direction. Let us take this as a minus here, minus 10 into 2. Now let us substitute. RA is how much? 17, 10 into 2. Now someone calculate how much you are going to get now.
48, sir.
Now this is what 48 kilonewton meter movement is experienced at this section, right? Experienced at this section, right? Now this is what considering the left hand side portion. Let us go for the right hand side portion. Then if it's correct, then only we can say component is under equilibrium condition. So now let us consider the right hand side portion here. Let us consider right hand side portion. I'll draw right hand side portion here. Now this is what RA. This is 30 kilonewton load. Now let us take a section here. Now distance is 6 meter here. Okay. So now this distance is 3 meter. Okay. Now what is the effect of reaction force RA on this beam at this location? Now I'll take a point here. Okay. Now if you fold it, now this load RA tends to move this in upward direction. Okay. This 30 kilonewton try to move this in clockwise direction. Are you agree with this one? Are you agree? So on right hand side, the reaction force is here. This is what RB not RA. 23 kilonewton. Try to push this beam in upward direction. Okay. And this 30 kilonewton try to push this in downward direction. So now you calculate what is the transverse force experienced by this beam at section XX. Okay. Now let us consider the transverse force experienced by this portion by this portion. Now what is the load? 30 kilonewton is acting in a downward direction. Let us take this as a positive. Okay. Okay. Now 23 kilonewton is there. It is acting in a upward direction. Let us take this as a negative. Now how much it is? 30 minus 23. You are going to get a 7 kilonewton.
7.
Okay. 7 kilonewton. So as we consider the sign conventions, let us take the downward force which is moving in downward direction is a minus, upward force is a positive. Okay. So how much you got here? 7 kilonewton. You got a minus 7 kilonewton here. Is it right? Now you just look out. We took here, okay. Now we have not calculated. Let us calculate force here. Now RA is try to push in upward direction. 10 kilonewton try to push in a downward direction. You got how much kilonewton? 7 kilonewton here also. Is it right? You got a 7 kilonewton. How much force you got here? You got a minus 7 kilonewton. Okay. So now let us go for the movement experienced by this portion. So now considering the right hand side. Okay. Considering right hand side. Now for earlier case, what you took? We took clockwise as a negative here, clockwise as a negative, okay. Sorry, anti-clockwise is a negative, clockwise is a positive. Okay. Now let us see what answer we are going to get. Now about this point, this 30 kilonewton tries to make the clockwise, okay. So this 60 kilonewton is try to make an anti-clockwise. So now let us take movements here. RB into 6 minus 30 into 3. Now 23 into 6 minus 30 into 3. Someone calculate how much you are going to get the value here.
48.
How much?
48.
48 kilonewton meter. 48
Yes,
kilonewton
sir.
meter. Okay. So now this is making in clockwise direction. Earlier it is making in anti-clockwise direction. Right? Earlier it is making anti-clockwise direction. Right? Now 48. Sorry, clockwise direction. Earlier this is in a clockwise direction. Okay. But here it is making an anti-clockwise direction. Right? You just look out. 23 into 6 is anti-clockwise direction. Okay. This is minus. If you go on for equilibrium conditions, so you got a majority is on positive side. We took anti-clockwise as a positive here, clockwise as a negative. But here what we took? Here also we took clockwise as a positive. Okay. Anti-clockwise as a positive here. Sorry, clockwise as a positive, anti-clockwise as a negative. Now the thing is that the section considered is subjected to the forces 7 kilonewton, okay, as a same. Either you consider from left hand side or either you consider from right hand side. 7 kilonewton is a force. Are you agree here? We'll discuss the directions afterwards. First you check out the magnitudes here. 7 kilonewton you got on right hand side. Okay. 7 kilonewton you got from left hand side. Are you agree? Equilibrium condition is same load banta left hand side or right hand side? Oh.
Yes, sir.
Okay. Moment is also same.
Yes, sir.
Okay. 48 kilonewton on left hand side. 48 kilonewton meter on right hand side also. You got the same load, right? Sorry, same movement. There is no any change in value. Okay. ಲೆಫ್ಟ್ ಸೈಡ್ ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಮಾಡಿದ್ರು 48 ಬಂತು, ರೈಟ್ ಸೈಡ್ ಕ್ಯಾಲ್ಕುಲೇಷನ್ ಮಾಡಿದ್ರು 48 ಬಂತು. ಯಾವ ಕಡೆ ಆದ್ರೂ 46, 45, 43, 46 ಹಿಂಗೆ ಬಂತ? ಇಲ್ಲಲ್ಲ?
No, sir.
ಓಕೆ.
No.
ಓಕೆ. ಸೊ ನೌ and moment also you got the same. The force is trying to shear off the section. Okay. Now coming to the magnitudes here. Coming to the magnitudes. Sorry, directions, not a magnitudes, directions. Now if you consider this left hand side portion, okay, you got a 7 kilonewton this try to push the component in upward direction. On right hand side, you got a 7 kilonewton, which is try to push the component in downward direction. Okay, downward direction, right? This is what a clear. Next, if you consider the movement here, this is what a force. Next, if you consider the movements here, okay. Now, I'll just draw some element here. Okay? Instead of complete, I'll go for element, small element. That is what a point. Now, on one side, this try to get a clockwise. Now, on right hand side, you got a anti-clockwise movement here. Okay. On right hand side, on left hand side, you got a clockwise movement here. Okay. On right hand side, you got a anti-clockwise movement. On left hand side, you got a clockwise movement. So now because of these two, your member is trying to get in this shape. Your member is trying to get in this shape. Okay? Right? Right. So now if you consider right hand side, you try to push the component in upward direction. If you consider left hand side, this is also making component to oscillate in upward direction. Okay? Now the force which try to shear off the component, the force which is try to shear off the component is called as a shear force. Is called as a shear force, and the movement bends the section. The movement which bends the section either in a concave shape or convex shape is called as a bending movement. Is called bending movement. Okay. So now force which is shear of section, shear of the section because of the transverse loads is called what? Shear force. Okay. So now due to this force what happens? So you try to bends the section. It bends the section. So the movement bends the section. Okay. Bends the section and hence may be called as a bending moment. And hence called as bending moment. Okay. Bending moment. So now let us come to the definition here. Let us come to the definition. Now shear force is a force. Okay. So shear force is at any section. Okay. Now I'll write the definition. Shear force at any section. Okay. Section is the force that is trying to shear off the section, share of the section, and is obtained as the algebraic sum of the all the forces. Just look out. Algebraic sum of all the forces, including reaction forces, including reaction forces acting normal to the axis of the beam axis of the beam, either to the left or right of the beam. Got it? Now shear force is defined as shear force at a section in a beam is the force that trying to shear off and is obtained as the algebraic summation of all the forces including reaction forces either to the left or either to the right of the section, so which are acting normal to the axis of the beam, okay? Which are acting normal to the axis of the beam. So what I got here, so you just added the forces, okay? So you just added the forces here, you just added the forces, you got some force, this force try to what, so try to push the component in downward direction. What portion you have considered here, you have considered here it is a right hand side, okay, or right hand portion. Similarly, in this case if you consider the left hand side portion, you consider left hand side portion. So now in this case 7 kilonewton is what, try to push up this component upward direction. So if the forces are one side it try to push up and one side it try to push down, then what happens, so component is going to be shear off, okay, component is going to be shear off, right? So now it is noted with the letter SF, it's noted with the letter SF, okay, capital SF. This indicates it is a shear force, okay? Shear force. Similarly, the bending moment, can someone generalize meaning bending moment? How you calculated bending moment in a particular section? How you calculated bending moment for left hand side or for right hand side? So how you calculated? Earlier you calculated? How you got a 40 kilonewton meter here?
Force and distance.
Force and distance. So what you done for particular position or particular point? What you done?
Multiplicating and adding, sir.
Multiplicating and
Adding.
adding. Right. So how we are going to define here bending moment? Now just added bending moments about the section. Is it right? Either considering from left hand side, either considering from right hand side. Are you agree with this one? Okay. So now let us look out here. So this bending moment is defined as bending moment at any section. That is what bending moment at a section, okay, in a beam, in a beam is the moment, is the moment that is trying to bend it, that is trying to bend it, okay, and it is obtained and it is obtained as the algebraic sum of the moment about the section of all the forces of all the forces including reaction forces including reaction forces acting on the beam acting on the beam either to the left or to the right of the section or to the right of the section. So some case you need to add up the external moments also, particularly for calculation of bending moment. If it's subjected to external bending moment, so you need to add up that one also. Okay. So based on the position, whether it's going to act on left hand side or whether it's going to act on a right hand side. Okay. So now let us look at the sign conventions here. Let us look over the sign conventions of a shear force and bending moment. So I already have seen one case. Okay. So it what one force try to push left portion upwards direction. So on the other side it try to push in downward direction. So this type of shear force is called as a positive shear force. Okay. Next, if the force which is there on left hand side, if it tries to push downward direction, and the force which is there on right hand side, if it tries to push in upward direction, then this is called as a negative shear force. Then this is called as a negative shear force. Suppose if the bending moment is tried to make and sagging form. Okay. Now this is what the shear force sign convention. Next, the bending moment sign conventions. If a bending moment try to form a sagging means just like an what do you call jogali. Okay. So if it tries to make a sagging, then this is called as a positive bending moment. This is called as a positive bending moment. If the bending moment causes a hogging, okay, hogging, so then this moment is called as a negative bending, right? The bending moment is positive if it tries to sag the beam, okay. If left portion of the beam is considered positive, moment works out to be clockwise. Okay? So that is what if tries to, let us take a point here. Let us take a point here. Now on this case what happens if the left side moment is going to be shown as anti-clockwise. Okay. So then you can say it is a positive. And about the point of a element or about the point of a beam, if left side portion tries to make an anti-clockwise, okay, anti-clockwise, then you can call it as a negative bending moment. Okay, that is what hogging bending moment. This is called as a sagging bending moment or positive bending moment. Okay, this is what hogging bending moment, and this is also called as an negative bending moment. Okay? Negative bending moment. Is it clear concept of shear force and bending moment?
Yes, sir.
Okay. So you have any doubts? Or you have any queries? I should give reply. Don't sit mom.
No, no, sir.
So now let us go for one small derivation is there. That is what is the relation between all these shear force, bending moment, and the rate of change of bending moment with respect to load, as well as the rate of change of load with respect to the displacement, sorry, distance. Okay, so that is called a relationship between load intensity, shear force, and bending moment. Okay, so let us go for the relation. So relationship between load intensity, okay, shear force, and bending moment. And bending moment. Okay, so here load intensity is what? F, shear force is SF, and bending moment is M. Okay, bending moment is M. So now for analysis, you just consider a simply supported beam which has a load of a variable nature, which has a load of a variable nature, not of a same nature. That is what? Not a constant load here, not a constant load. So now I'll draw the diagram. Now let us consider this as in support A and support B. Okay. So now this is what the variable load. Okay. So now for this one, you just take L as the length, L as the length. Okay. So now for analysis purpose, what I'll do, I'll take a small element here. Okay, I'll take a small element which has a length of dx or delta x. Okay, which is there at a distance of x from left support, which is there at a distance of x from left support. Okay, left support. Now let us consider the forces which is acting in downward direction is of a positive nature, as well as the movement which is going to get because of this moment, because of this load is also as an positive one. Okay, as also positive one. Okay, now what I've done, we made a small element consideration here. Okay, which has a length of delta x, which is length of delta x. Okay, Now let us take. So I'll draw the clear diagram for the element, the shear force as well as the bending moment. Okay, the shear force as well as bending. You have any query? You have any doubt? So now as you consider, so the intensity of force, shear force is of what? It's a positive. It is to be positive. Okay. So now this element is try to push in downward direction. Okay. So now this side it try to push in upward direction. Okay. Now the movements which are going to cause here, this is what for this element. Okay. For this element, that is what element length is dx. Hmm? Element length is dx. Now I'll go for little enlarged view for that element. Enlarged view. So now let us take an intensity of load, okay, which is try to push in downward direction as F. Okay, F. The bending moment which is there on this left hand side as M. Okay. Now if you consider the load here, let us go for load. Now as to be this component in then positive sense, okay, the force which is act on this direction is also an positive of value F plus delta F. Okay, and bending moment M plus delta M. Okay, then only this element is under positive condition. Then only this element under positive condition. Okay. So now if you consider the intensity of loading is to be constant, okay, so now considering the equilibrium condition of the element, okay, so let us go for the summation of forces. Let us go for summation of the forces. Okay, so now let us take a W here. W, W is what the intensity of load. Okay, so intensity of load, this is what per unit distance. Okay, so unit is let us take it as a Newton per meter. Okay, you can say unit length. You can say unit length. Okay, so now let us write the diagram, write the equation here. So F, which is acting in downward direction, sorry, F plus delta F, which is acting in a positive. Okay, now the force is there, F is acting in a negative direction. Negative direction. So now intensity of load because of this variable load. Okay, so now distance is how much here? It is delta x. Okay, now intensity of load is W minus W into delta x. This should be equal to 0 for equilibrium condition. This should be equal to 0 for equilibrium condition. Okay, so now if you simplify these equations, what you are going to get? So you are going to get, so W equal to delta F by delta x. Delta F by delta x. So this is called as the intensity of load per unit length, where W is what is load intensity per unit length, per unit length. Okay, so in the limiting case, if delta x tends to 0, in the limiting case if delta x tends to 0, So then the above equation will become, so df by dx equal to w. Df by dx equal to w. In the limiting case, I'll write here, in the limiting case, if delta x tends to 0, okay, so let us notify this as equation number 2. Okay. Similarly, now it has to be under equilibrium state for the moments. It has to be under equilibrium state for the moments. So now if you consider the moment of the element about the right phase, okay, now taking moment of the element about right phase, about right phase. So what will get, m plus delta m minus m plus delta f into, sorry, f into delta x, okay, plus w into delta x into delta x by 2 equal to 0. Okay. So if you neglect the higher order terms, so we're going to get delta m plus f delta x equal to 0, okay, or f equal to minus delta m by delta x. Again, so if we limit in the limiting condition, in the limiting condition, okay, if delta x tends to 0, then this load f equal to, so minus a dm by dx, minus dm by dx. Now these two are the relations. What is the one relation here? So the intensity of load, okay, is going to change with respect to the distance, okay, with respect to the distance, as well as here the shear force or the force which is there, okay, is also in correlation with the moment. Okay. So third term students, you just put the attendance in chat box and you will leave the class. If some students, you just wait for 2 minutes.